Hello, everyone. I'm going to talk about our paper on cluster editing parameterized above modification-disjoint P₃-packings. My name is Shaohua Li. This is joint work with Marcin Pilipczuk and Manuel Sorge. Cluster editing is a classic NP-hard problem. This is the formal definition of the parameterized version of this problem. In this problem, we are given a graph G and an integer k. The task is to decide whether we can get a cluster graph by at most k edits. Here edits means edge insertions or edge deletions. The simple observation is that G is a cluster graph if and only if there is no induced P3 in G. Cluster graph is FPT parameterized by the size of the solution, and this is the running time of the fastest algorithm for cluster editing now. A natural question is that, is this problem still FPT if cluster editing is parameterized by the difference between the size of the solution and the lower bound? When Bevan et al. Started this line of research and showed that if the lower bound is the size of the vertex disjoint P₃-packing, then the answer is yes. In this paper, we study another variant such that the lower bound is the size of a packing H of modification-disjoint induced P3s. Here, modification-disjoint means not sharing edges or non-edges. The size of H is a lower bound of the solution because a solution S must contain one edit for every P3 of H. The open problem is CEAMP's FPT parameterized by L? Here, we call L the number of allowed excess edits. This problem is proposed by Komoshevich at Saarland meeting. We have two results in this paper. The first result is that cluster editing about modification-disjoint P₃-packing is NP-hard even for L equals 0. The second result is that cluster editing above two restricted modification-disjoint P₃-packing is in XP. Here, two restricted means that every vertex belongs to at most two P3s of the packing. First, let me introduce our NP-hardness result. Our NP-hardness result starts from a 3-set instance. We show that in polynomial time, we can construct an equivalent instance of CEAMP. First, let us do a warm-up exercise. Suppose that we are given two cliques A and B. How to cover all vertex pairs between clique A and B using modification-disjoint P3s. So this is the solution. Then let us go one step further. Suppose that we are given three cliques, each of size 5. The question is how to cover all vertex pairs between A and B, between B and C, using a set sigma of modification-disjoint P3s, such that by the size of sigma edits, we can either merge A with B, separate C from AB, or merge B with C, separate A from BC. So our solution is let A, B, C be variables from the finite field gamma of size 5. Let A, B, C be the labels of vertices from A, B, C respectively. Then we create a P3 ABC if A minus B equals B minus C. This is part of the solution. So with that tool in hand, we can construct the variable gadgets as follows. Let Mi denote the number of clauses that contain the variable xi. For each variable xi, we create 4 Mi vertex disjoint cliques with 5 vertices each. For every 3 consecutive cliques, we connect them in the way described in last slide. Here we identify the first clique with the last clique. Thus, the cliques are connected into a cycle-like structure. Because of the construction, we have to merge either every pair, we call it even pair, or every odd pair. For each variable xi, we fix an arbitrary ordering of the clauses that contain xi. If a clause gamma j contains xi, that pi ij denotes the position of gamma j in this ordering. Next, we go to the skeleton of the clause gadget for clause gamma d. This picture shows the skeleton of the clause gadget. In this picture, the cycle-like structures represent variable gadgets. For example, this cycle represents the gadgets for xa, and this cycle represents xb. This cycle represents xc. The thick brown edges represent the connections between variable gadgets and the clause gadget. The green P₃s belong to the packing and keeps basic constraints. This means that if we delete this side of the first green P₃, then this side of the green P₃ becomes undeletable, and so we have to merge these two cliques. For the second P₃, if we delete this side of the P₃, then we have to merge these two cliques or these three cliques. For the third green P₃, if we delete this side of the P₃, then we have to merge these two cliques. So we can abstract the merging model for a clause gadget gamma d. The merging model is a guide for cliques to merge or separate. A vertex in this picture represents a clique in the skeleton of the clause gadgets. If there is an arc between two vertices, the two corresponding cliques can be merged. A triangle means that the three cliques corresponding to the vertices can be merged. For example, these two cliques can be merged, and these three cliques can be merged. However, these two cliques cannot be merged. I want to mention that in this picture, the number represents the level of the cliques. This is not the number of vertices in this clique. So let's go to the details of the connection between variable gadgets and the clock gadgets. In this picture, the bottom part represents part of the variable gadgets, and the top part is a clique in the clause gadget. When we add the first red P₃, we will break the P₃ that already exist in the variable gadgets, namely V3, V1, V8. So this edge V1, V8 becomes vacant now. When we add the second P₃, the edge V5, V2 becomes vacant now. And when we add the third P₃, this edge becomes vacant now. However, we can create a new packed P₃, namely V2, V6, V5. Finally, we add the fourth P₃, and this edge becomes vacant now. And we can create a new packed P₃. Actually, we will show that we can find a C8 in these two parts. And we will use this C8 in the later stages of the construction. Next, we go to the implementation of the merging model. We will decide the exact size of every clique from level 0 to level 4 to implement the merging model. The base case is that cliques of level 0 have size 5 and cliques of level 1 have size 1. We need some algebraic tool in next step. Our algebraic tool needs to solve three questions. Let P be a prime number and let B be a complete bipartite graph such that the size of V equals P, the size of W equals 2P. Question 1 is, how can we cover all vertex pairs between V and W by a set of modification-disjoint P₃s or triangles? Question 2 is, how can we avoid conflicts if we are already given some initial packed P₃s and C8 between V and W? Question 3 is that, how can we make sure that W is connected even if we remove the packed P₃s, since we will use W and the building block to merge or separate in reduction? Next, let me introduce our idea. First, we partition W into two parts, W and W prime of size P each. If a P3 W prime already exists, we put W and W prime into two different parts, like in the picture shows. If a C8 already exists, we expand the C8 and in the following picture. This is the C8 we have already seen. And we will expand it like this. So how do we cover the vertices here? First, we label the vertices of V, W, and W prime by elements of the finite field of size P increasingly. The labeling of the vertices of C8 and P3 are as in the picture. Let VA belong to V, WB belong to W, and WC prime belong to W prime. We pack the triangle VA, WB, WC prime if A minus B equals B minus C. We will show that the packing coincides with the existing C8 and P3. This is part of the solution. We will see that finally they coincide. Finally, we want to mention that the edge WI plus 4 and W prime I plus 4 is still not covered by any packed P3, because in our construction, these two edges are actually belong to two different packed P3s. So finally, W is still connected. Then, with this algebraic tool in hand, we can finally implement our clause gadget. So the base case is that clicks of level 0 have size 5 and clicks of level 1 have size 1. For each click Q of level I, let V be the union of clicks adjacent to Q, which are of lower levels. Let P be the smallest prime such that P is at least the size of P, V, and then we add P minus size of V dummy vertices to V and apply the algebraic tool. With this procedure, we can see that this vertex of level 2 has size 4. And this click of level 3 have size 14. And these two clicks of level 4 has size 34. This click of level 4 has size 46. Then let us go to the completeness of this reduction. First, we show that suppose that we are given a clause gamma D. And suppose that we are given a satisfying assignment. Suppose that the variable xi is set to true. Then we merge all the odd pairs in this variable gadget. Otherwise, we merge all the even pairs in this variable gadget. Since it is satisfying, so for this clause, there must be at least one variable which satisfies it. If there are more than one variable satisfies this clause, then we choose one variable arbitrarily. Suppose that we choose XA, that is XA satisfies gamma D. Then we merge TDA and QD1. We merge QD2, QD3, and QD4. The operations are shown in the picture. If XB satisfies gamma D, then we merge QD1 and QD2. We merge QD3, QD4, and TDB. If XC satisfies gamma D, then we merge TDC and QD4. We merge QD1 and QD2 and QD3. The operations are shown in the picture. Finally, we will see that after all these operations, our given graph becomes a cluster graph, and the number of edits is equal to the size of the packing. So next step, let's go to the soundness of the reduction. For the variable gadget of xi, we will claim that either the even pairs are merged, This means that we set xi to true, or the odd pairs are merged. This means we set xi to false. Since QD1 and QD4 are connected but not adjacent, so at least one of the following three cases hold. Case 1, QD1 and QD2 are separated. Case 2, QD2 and QD3 are separated. Case 3, QD3 and QD4 are separated. So let's first go to case 1. QD1 and QD2 are separated. Then, according to the constraints of the green P3, the TDA and QD1 are merged. Since QD1 is not adjacent to the click in the variable gadget of XA, then TDA and this click in the variable gadget are separated. And since the Brown structure, these two pair of clicks are merged. So this means XA is assigned to true. The operations are shown in the picture. In case 1, XA is assigned to true and it satisfies gamma D. Case 2 and case 3 are similar to case 1. If case 2 holds, then XB is assigned false and satisfies gamma D. If case 3 holds, then XC is assigned false and satisfies gamma D. This finishes the NP hardness proof. Our NP hardness result implies that CAMP is probably not FPT or even EXP unless P equals NP. This motivates us to study a more restricted variant of CAMP, in which every vertex is incident with at most 2 packed P3s. Here is the formal definition of CATMP. We want to mention that this definition is very similar to the definition of CAMP, except that every vertex V is incident with at most 2 packed P3s. This is the main theorem in this part. Cluster editing above 2 restricted modification-disjoint P3 packing can be solved in polynomial time. We will use this theorem as the main tool. We will introduce the algorithm for the case of L equals 0 briefly. We define protoclusters as the connected components of the graph obtained by removing the edges of all packed P3s. We define 4 types of P3s as follows. Every ellipse in the picture represents a protocluster. This is type alpha P3. This is type beta P3. This is type gamma. And this is type delta. Reduction rule 1 says that for any protocluster C, if there is a non-edge which is not covered by any packed P3, then return no. Reduction rule 2 says that if there is a type beta or type delta P3, then insert an edge to this non-edge and remove this P3 from the packing. Here is an example. Reduction rule 3 says that suppose that we are given 2 protoclusters A and B, and if there is a non-packed non-edge between A and B, and there is a packed edge between A and B, then delete this packed edge and remove the corresponding packed P3 from H. Here is an example. Reduction rule 4 says that we will do brute force on every component of size at most 6. Reduction rule 5 says that we will remove all isolated click. This lemma says that after applying reduction rules 1 to 5 exhaustively, if the algorithm did not return no, then there is no protocluster of size at least 4. So next, only protoclusters of size at most 3 remain. We have reduction rule 6 to deal with the case in which there is a protocluster of size exactly 3. This is an example. Here, A is a protocluster of size 3. B and C are protoclusters of size 1. Here, we delete this edge here, and we insert this edge. Then we remove the P₃s from the packing. Our next task is to study how the protoclusters of size 2 and 1 can be combined. Let S be the solution. We will focus on the structures of C6, C5, and C4 in the final cluster graph. The following is an example of the possible structure of C6 in the final cluster graph. The following are some examples of possible structures to form a C5 in the final cluster graph. The following picture shows an example of possible structures to form a C4 in the final cluster graph. According to the structure in the previous slide, we get reduction rule 7 to deal with the structures to form a C4 in the final cluster graph. The following pictures show some examples of reduction rule 7. After applying reduction rules 1 to 7 exhaustively, the sizes of the cliques are at most 3 in the final cluster graph. After applying all these reduction rules, we show the remaining instance of CATMP is equivalent to an instance of a variant of cluster deletion, which only allows edge deletions. Then we show this instance of CDAMP can be reduced to an instance of 2-set, which can be solved in polynomial time. This is our main lemma for the reduction to 2-set. So let's conclude with some open problems. First, is there an FPT algorithm parameterized by L for cluster editing above to restrict modification-disjoint P₃ packing? We have shown this problem is in XP. However, it is still possible to be FPT. So we need more structural insights into this problem. The second problem is, what is the computational complexity of other variants of cluster editing above modification-disjoint P₃ packing? Here, every vertex V is instant with at most C packed P₃s, and C is between 2 and 23. Okay, thank you for watching.